one, I'm going to close that drawing. And I'm going to go ahead and open the other path, I call it. Great book by DeSoto. But the other path here is going to be this drawing where essentially I've laid it out showing you how to do the moment arms. I haven't done the circles in this one, but be aware that really that's what one way to look at it, though it can get confusing here when you're laying this out. In other words, you've got a moment arm along here that's defined by a circle and a moment arm here. It's a ratio of the distances of the circles defining the circle's tangent to the force. And if you think about this force is up here, this force is that line of force, you can think about it that way. Let's do problem 1. Once again, we've got to make sure I get my layer states and my views. I'm going to go to my layer state. That's the as stated. I'm going to go to problem 1. Let me see what I say. Well, there's my solution about, if we look at here, this is my force times distance equals force times distance about this. So that gets your solution here. And that one kind of shows you where the moment arm is there. So force, this is spinning this way, so this has to spin up. The ratio of that distance times that force divided by this distance gets you the solution. That's probably the best way to do it no matter what, because you can also pull out triangles and do this and measure by hand. Let's go to problem as stated, problem 2. There's problem 2, really not much to that one, but if you think about it, force times distance equals force times distance. You could do the same thing there. There's your moment arm. So this force times this distance is going to equal to this force times that distance. That'll turn out, of course, to be the same as the y component there. Go to problem 3. You see that one there? As stated. Now you've got effectively about A, you've got force times distance for this force equals force times distance there. In other words, this force times this distance has to be the reaction at B times the distance in between. When you're solving about B, you have this force times distance needing to be equal by a force times the distance here. That, of course, is going to be down. And here within, it's pretty straightforward. Very often, if they're straight up and down, you don't need to draw the moment arm. You know that the moment arm is a vector that has no z. It just goes from here to there, and you're back to that kind of splitting it based on distance between the other support. So I'm going to go back to the next problem. As stated, problem 5. It's going to be the same thing. Force times distance equals force times distance. Of course, in each time you're solving for the unknown being the reaction, so you want to sketch up that one unit vector so you can see that the circle is there. So I'll draw the circles on this one. If you're looking at this force here, a circle here from the, and I think these are defined at the end point, tangent to the line of force. So that, if I list that one, so that has a radius of 13.75. That's the length basically of that. 13.7 times the full force divided by the 20 between gets you the reaction at this support to that. If I do it the other way for the next one, or for the other force, circle from the end point there, tangent to the line of force compared to circle from the end point there. Got to be careful with all these endpoints. To the end point there, we have our ratio of circles. And you realize that this, of course, is a lot less. It's farther away. We'll go to problem 6. Same thing. You see how the moment arms start to shorten up. In other words, force times distance. In other words, this magnitude of force times this distance is going to be this distance times the perpendicular force out there. So you take basically this distance times the force divided by the distance between the supports, and that gets your reaction to this one particular force. Problem 7 as well can be done, though this one you can see is probably not a bad one, and I'm just going to cheese it in here. You could go ahead and add these two together if you would. If you can slide this up along its kind of line of force here, right? See that there? I kind of slid that up. And I can slide this one down. Left click, space bar to there. And then I can take this one and add it. Now I have my resultant, which is this. And now I can just do one force times distance problem from the end point there. Tangent. That's how straightforward these problems can be if you start thinking creatively about simplifying before doing every individual force. Though in all reality, let's go and show that you couldn't treat them individually. I'm doing a bunch of undos here. Your moment arms are here. In other words, force times distance on the little tiny force. That arm, as you spin it around, turns out to be pretty close to that. So almost all the force gets kind of sucked up there. And then it has a list force as a little tiny arm about here, so it has very little reaction to it back here. That one, however, would be much better stated and solved by kind of solving and doing a simplification of those two vectors based on the slide to the concurrent point. That's 8. Same thing here. You could do some sliding, but we'll go ahead and show you that, in fact, you've got a force times distance for that equals a force times distance for this. The circles, these of course are just, once again, can be split based on that general rule. It's still the same moment arm circle rule. Problem 9. As stated, force times distance. I'll show you the circles here in this case. From the end point there, tangent to that line of force is one circle, and the other circle is from the end point here to the end point, which is tangent to that normal force there. So you have your ratio of circles, and you see the 2 to 1 there. And finally, problem 10, which is the same thing. Realizing that only the pin joint can react parallel to the surface. A roller joint only reacts normal to the surface. So that is all those problems. You'll have a chance on Wednesday to go through very, very similar problems using all the tools you have, and I would really suggest that you and know that you must then be required to solve by the moments and then check by the forces. Take a look at these and talk to me on Tuesday if you cannot go through problems like this, and the tools, they're all pre-drafted. You should be able to do these almost just as quickly by using a scale. Thanks for listening.